All right, so in part one, we talked about something called the law of sines, which is one of the ways that we can solve for missing pieces of non-right triangles. And in this video, I'm going to derive another relationship for you called the law of cosines. So the good news is it pretty much starts off the exact same way. So I'm going to label this. Remember, all of our angles get capital letters. All of our sides get lowercase letters. And I think this one here was orange. And I believe I also added a height or an altitude for you. Okay. And I called it H. Okay. And remember, up to this point, we've only studied right triangle trigonometry, so we don't really know anything different. So we're going to have to rely on that right triangle trigonometry, the sine, the cosine, the tangent, and in this case, you're going to see the Pythagorean theorem makes a comeback in order to derive some of these relationships. If you look at the relationship from above, notice that our final answer only had pieces of the triangle, lowercase a, capital A, lowercase b, capital B, lowercase c, capital C. Sorry, those look kind of similar, but one's capital, one's lowercase. So same thing here. We need another relationship that holds true, but only uses the A's, the B's, and the C's. So any other letter that we introduce needs to eventually go away. So the trick with the cosine law is, well, A, it uses cosine, and B, it also makes pretty good use of the Pythagorean theorem, which we haven't really talked about for a while. So in order to make use of the Pythagorean theorem, I'm going to split it up like we did before into two smaller triangles. Again, notice this one on the left is kind of skinnier triangle. So that's going to be this one. They're not drawn to scale. I just pulled off a random triangle from the internet. So let me write what we do know. So what we do know is that's capital A, same as right here. We also know that the hypotenuse is lowercase b. And we also know that this is h. And if we go to this other triangle over here, this one in green is going to be this part of the bigger triangle. And so again, what do we know about that one? We know that the hypotenuse part is lowercase a. We know this part is lowercase b. And we know that the height is h, right? So you're probably wondering, why am I not labeling some of these other pieces? Well, if you notice up here at the top, this C got chopped up. These two angles represent capital C, and I only took a piece of that. So it would be misleading for me to call that C. So I'm not going to call that C. And then same thing down here. It's kind of misleading I can't call this C because C is the whole thing, and I'm only looking at a piece of it. So that would also be misleading. But one of the tricks to this one is in the law of sines example or derivation, I didn't really pay a lot of attention down here to the base of the triangle. But in this case, I am going to pay a pretty good amount of attention. So I'm going to get a little purple piece, and I'm going to say, let's say we know this is x, right? X is some arbitrary value. So that means this down here is going to be x, right? And if that's x, we should be able to express this little piece based off c, lowercase c, and x, right? So to kind of illustrate this, I'm going to do a little red example. Let's say we knew that the whole distance of the bottom was 20. And let's say I knew this little piece right here was 5, right? You probably would be able to figure out that this piece here is 15 because it's the same as 20, the whole, minus the small piece that I know, right? If I use that same logic, then I'm going to also be able to see that what was 20 in this case, right, came from C. So C, I can also write this as C, that would be the 20, minus 5 would come from the x. right? So whatever the full length is minus whatever that piece is. So that's how we're going to express the bottom piece of this. Let me get rid of this. That was just to illustrate the thinking. Oops. Okay, so then this piece is C minus X, which is going to go in this part of the triangle. Okay, so it's no secret that if we're going to be using the law of cosines, sorry, I never really said that we were doing that. Law of cosines. So if we're going to be doing the law of cosines, obviously we need to figure out the cosine of something. Whereas in this earlier one, see how we found the sines? In this case, we're going to be looking at the cosines. Okay, so let's do this. So in this example, my reference angle would be here. That's the only angle that I truly know in this triangle. So if I go across from the right angle, that would give me my hypotenuse. If I go across from the reference angle, that would give me my opposite. And my leftover one would be the adjacent. If you know your SOHCAHTOA well, SOHCAHTOA, right? And we know that we need cosine, that would be the middle acronym. So we know that we need the adjacent and the hypotenuse. So we do not need this one. So we could say the cosine of angle capital A is equal to X over B. And if we do a little quick, let me just go down here real quick. If we do a little quick cross multiplication, let me do it here. We could say 1 times X, or X, is equal to cosine capital A times B. But I'm going to write it in this order just so that we don't confuse the location of the lowercase b. Okay, so far that is one relationship that's going to come in real handy in a bit. Okay, second big relationship, friend of ours. So we're also going to need, we're also going to need the Pythagorean theorem in this case. So for those of you that don't know, I don't know why this is freaking out. Okay, Pythagorean theorem. Okay, so we know it as a squared plus b squared equals c squared, right? But in our triangle, we don't have a, b, c. We have x, h, and b. So just remember that c is the hypotenuse. In our case, the hypotenuse is here. Just remember that that is what we're technically calling c in the equation. So from this triangle, we could say x squared plus h squared equals b squared. And that is going to be a very, very important relationship in a second as well. Okay. Now we come to the bigger triangle. And again, we're going to use our friend, the Pythagorean theorem. We're going to use our friend, the Pythagorean theorem. And this one's going to be a little bit more complicated just because this side is a little bit interesting, the c minus x, but we can do it. So a squared plus b squared equals c squared. So again, notice that this is the side that we want to call c because it's across from the from the right angle. So that's your c. So we would call this c minus x squared plus h squared equals a squared. And hopefully you remember your Punnett squares or however you FOIL or whatever, but I'm going to do this real quick for the sake of time. This is going to simplify to c squared minus 2cx plus x squared plus h squared equals a squared, which looks really ugly. Now I want to remind you from the beginning, we want our final answer to only have, like if you look at the sine law, we want it to have a's, b's, and c's. So capital C, lowercase c, capital B, lowercase b. Right now we're in a little bit of a pickle because we have x, and we have h. Now there is some good news though. If I rearrange this, so I'm gonna just change the order a bit. I'm gonna call this x squared plus h squared plus c squared minus 2cx equals a squared. Now here, this should look a little familiar. The x squared plus h squared, that actually came from here. So you'll see that same x squared plus h squared right here. And notice that according to our equation, we can also call, or another name for x squared plus h squared is b squared. So wherever this box is, I'm actually going to call it b squared plus c squared minus 2cx equals a squared. Okay, so we made it a little bit more simple. Now we still have one more issue. We have x, and we only want a's, b's, and c's. However, if we look down here, it erased. If we look down here, at one point we had cross multiplied and we had found another way to say x was b cosine of capital A, which came from here, right, from the cross multiplying. So right here, I actually have another way to say that. It is b cosine capital A. And then I can write the rest. Ta-da! So this, believe it or not, is the law of cosines. Now it looks a little ugly, but I'm going to hopefully give you some tips and tricks to remember how the structure of it. So it actually comes in 3 flavors. Same exact formula, just the whatever letters you choose are different. So here's the first one that we did. So notice we have a squared, right? So think of this kind of like a Pythagorean theorem, just with the letters all kind of out of order. So normally it's a squared plus b squared equals c squared, like this. But this one's out of order, and a squared's by itself. So it's going to be a squared equals b squared plus c squared. Now, the second part you're going to add, so you're going to put minus 2, and then you're going to repeat the letters that came from that second part of the Pythagorean theorem. So see how mine is b and c? So mine's going to be minus 2bc, and then you're going to put cosine, right? You need a cosine at some point because it's called the law of cosines. And where you're going to get that letter from? It's going to come from the beginning. So see how this one was lowercase a? Now it is capital A. So that is flavor 1 of the law of cosines. Okay, I'll do it 2 more times. So if you want flavor 2, let's say you started with b squared. B squared, think of it like a Pythagorean theorem. A squared plus c squared, but just out of order. Then minus 2, where you're going to get those letters from, right here, right before. AC cosine was lowercase b, now it's capital B. And that would be flavor 2. But notice it's the exact same thing, just different orders of the letters. And then last version, c squared, pretend it's a Pythagorean theorem. A squared plus b squared. Then you're going to do minus 2, which letters? The ones that came right before, times cosine of, it was lowercase c, now it is capital C. And those are your 3 flavors of the law of cosines. Okay? Don't think of them as 3 separate formulas. They're literally the exact same thing. So it's just depending on where you start in the triangle. When I do some examples, I'll tell you what I mean. So this is the law of cosines. Okay? All right, so in a future video, I will be showing you how to use this law.